On this week's show, Jem visits the future of recycling.
They've installed this ingenious device here. It's like an electronic eye that's linked up to a compressed air shooting gallery.
Dr. Yan gets all theatrical.
Take a look at this. Good, isn't it?
And Dallas gets very excited about GPS.
This device can tell you the range within 3 or 4 millimetres. That's unbelievable.
That's Bang Goes the Theory, revealing your world with a bang.
Hi there and welcome to the show. First up, this.
Turn around as soon as possible.
Not the sat-nav lady, but the amazing technology behind the sat-nav lady, GPS. It's up there.
About 8,000 times a year, volunteer lifeboat crews like this one get sent out all around the waters of the UK and the Republic of Ireland to perform rescues. But each time they go out, they rely on one fact, that 12,000 miles that away, in what's called a mid-orbit, a 27 global positioning satellites. Okay. How much more difficult would your job be if you didn't have GPS?
With the GPS, you get a casualty called up, you've got their position straight away, put it into the satellite system, gives us range, bearing, distance to run, gets you to where you need to be straight away. Time is lives, absolutely vital to our saving work.
The American GPS satellites work alongside another Russian system called GLONASS. And to explain all, I'm meeting a GPS expert at a satellite tracking station in East Sussex.
How does it all work? When I punch in an address here and press go, what's going on? So the first thing the device is doing, it's measuring the distance from here, from the receiver, out to those satellites. Second thing it's doing is tracking these signals broadcast by the satellite, which is telling the box where the satellites are up in space.
So this is just like a radio receiver, if you like, picking up sort of radio signals, but these radio signals have data in them coming from satellites.
Exactly,
Okay.
that's right. So the satellite spits out a little blob of electromagnetic energy,
Right.
and on that is like a time mark. It says, okay, I transmitted this signal at this time, and then as well as transmitting the time, it says roughly this is where I was when I transmitted the signal.
So you've got a very, very accurate clock in there.
Very, very accurate clock, yeah. And the receiver down here has also got a clock in it.
Yeah.
So let's just take the phone here, for example.
Okay.
Okay. So there's a clock in here. There's a clock in here.
Yeah.
When the signal leaves the satellite, eventually, sometime later on, about 77 milliseconds later on, in fact, this picks it up.
Right.
Then the receiver takes a reading of its clock when the signal arrives.
Yeah.
So the signal, the receiver knows when the signal got there, and it knew when it was transmitted.
So I now know where that satellite is.
You know two things. You know where the satellite is,
and what time,
and you know how far
away
you
it
are.
is. Okay.
Right. That's basically it.
Wow, you know what's just struck me is just quite, this fantastic infrastructure that supports all this in terms of satellites, in terms of ranging stations, in terms of big physics, in terms of big mathematics. And every time I turn one of these on in the car, I get a bit cross because it doesn't sort of work instantly. It's amazing.
So why 27 satellites in orbit? Well, actually, it takes more than one to give an accurate location. In fact, it takes 4.
Imagine these are 3 satellites. So we've got a pink satellite, a blue satellite, and a green satellite. And we know the coordinates of where they are out in space. And the ropes represent the ranges.
We know the coordinates out in space because they've got very accurate clocks, which we can measure the time it takes to beam the signal back to Earth.
That's right. So the rope represents the range.
Okay.
So let's see what would happen if we had just one satellite.
Careful of your nice shoes.
Yeah.
Ah, okay, so with one satellite, we could be anywhere on this line, basically.
Exactly.
So,
right.
Which is not much good.
So I know my receiver could be here, or it could be here. That's using one range from one satellite.
Let's bring in another satellite then. Ah, because we've got 2 satellites where these points intersect.
That's right.
There, that's where we are.
So in 2 dimensions, that's going to be your position fix.
Yeah.
Now, of course, in reality, in space, we're trying to fix our free coordinates. So maybe so much along X, along Y, along Z, or eastings, northings, and height. So we need to make a measurement to a 3rd satellite. Let's do that. So suddenly we have where these points all intersect. This is our location in 3 dimensions.
That's right, that's right.
OK, that seems pretty convincing. But where does the 4th satellite come in?
You use the 4th satellite to synchronise your little clock with the space clocks. The problem is to do with the quality of the clocks, because the clocks up on the spacecraft, they cost about $2 million each, and they're really, really good, really stable. The clock in your little GPS receiver only costs about 15 cents, and so it really doesn't keep time as well as the clocks up on the satellite.
So the 4th satellite really just there to as a sort of get rid of those margins of errors, get rid of those problems you've got.
And to make sure the satellites really are where they say they are, tracking stations like this one constantly fire lasers at them as they pass overhead.
Dallas, fire that laser.
OK, I'm going to fire the laser. Ready? So really what we've got here, we've got a giant laser pointer, if you like. On the satellite, they've kind of got reflectors like cat's eyes. You ping the laser at the cat's eyes, it bounces the laser back. We know what the speed of light is, so we know where it is.
This device can tell you the range within 3 or 4 millimetres.
That's unbelievable.
Yeah, it's pretty cool engineering.
Amazing. It really is. The question is, what now for the next generation of satellite navigation?
Well, it's about to get even better. The European Space Agency is launching its very own answer to GPS, Galileo, which will see 30 new navigation satellites in orbit over the next 5 years.
I'm quite nervous, actually. We're quite a privileged position here. We're one of the very few crews who've actually been allowed in here. Behind that door is a very top-secret room where they're building Galileo. We all use the American system at the moment, GPS, and that's 30 years old. And Galileo is the new generation that proves to be more reliable, more accurate to cope with the demands of the future.
Dr. Mike Hughes is leading the development of the system and shows me the inside of one of the new satellites.
Let's start at the beginning. Why Galileo? Why do we need this? Because we've got a GPS system up there already.
There are limitations to the accuracy of GPS.
Yeah.
There are limitations to its availability, and the European Union took the decision that we were becoming too dependent on a system we didn't control. I mean, GPS is a monopoly system.
And it's an American system.
And it's an American system. Right. And even being a trusted partner.
It's probably useful to have your own just in case. Is there one thing that makes this
thing
that
that really stands out, I think, is the clock technology, the precision of the clock technology. We have actually 4 clocks here. There's 2 mesas. These are the big, shiny silver boxes.
Yeah.
And 2 rubidium clocks.
Right. And these are sort of atomic clocks, like super accurate clocks.
Yeah. So the mesa, for instance, takes 3 million years for that clock to lose 1 second.
That's pretty accurate. The clocks that are up there at the moment, the ones that are on the GPS system, just by way of comparison,
they're about 10 times worse than that, so they're still pretty good, and that's the rubidium clocks, so about 10 nanoseconds per day.
Yeah, so better time, better accuracy.
Yeah.
It's funny to think that GPS, once designed as a military application, has changed our lives to the point that we just completely take it for granted. But what I find exciting are the future applications, the things that nobody's yet thought of that Galileo could be making a reality.
All right, officially, my absolute favourite outfit you've ever worn on Bang. Can we just please see that shark up again? It's a thing of beauty.
It's not great, I
love it.
It's hardly a conventional jacket you're wearing yourself, Liz.
Shut up.
I'm not going to pass comment. Anyway, all those Galileo satellites are going to be blasting off October this year from French Guiana, I believe.
So when are we going to be able to use them? When will they become fully operational?
Probably round about 2014.
And does it mean that the sat-navs in our cars will be more accurate or get a better signal or something?
I think that's a really good question. I don't think it's even to do with the sat-navs in our car. I mean, they're pretty accurate, or as good as they need to be. They could be a little bit more accurate. It's more to do with things like plate tectonic activity, things that need a much greater degree of accuracy, things like measuring the Earth's sea level, things like measuring electronic financial transactions that you need a really, really important timestamp on, things like that. More importantly, the things that no one's even thought of yet will be able to be made possible, facilitated by the Galileo
See, that's the thing, isn't it? It's all about sort of all of science, our infrastructure, economics, relying on this technology.
Yeah, absolutely.
So if there's one thing better than knowing where you are. It's knowing exactly where you are.
Exactly. The other good thing about the Galileo system, it's got an inbuilt search and rescue feature designed into it. So if you're lost at sea, not only can you beam up a distress signal, you also get a reply back straight away that your signal's got there. So it's good. It's
something
really
that those RNLI boys will be putting to good use, I'm sure.
Absolutely. Now, we all know that satellite technology has revolutionised the world, but we thought it might be fun to have a look at some other technology that might be doing the same in the future.
Which is why...
Well, I didn't want to ask.
I'm wearing this. Do you like it?
I love it.
It's my new favourite jacket.
Like it.
This is part of a whole new host of wearable computers that are going to become part of our lives in a very real way very soon indeed. Now, this particular one is designed to help me play the violin better. I say better. I don't even know how to play in the first place, so it's got its work cut out. It's been developed by the people at the Open University, and it's a combination of motion capture and vibrotactile technology. Oh yes, and it's full of like sensors and little vibrators, the same vibrators you use in mobile phones, so that if I have the position of the violin or the bow in the wrong place, it goes off. Okay, so if we turn on the machine and I start playing, it's already gone off. Not only does it vibrate in the arm that's wrongly positioned, it vibrates around my waist as well. And if I try and play, but don't have the bow in the right place, it goes off. Or if I lower the violin, it goes off as well. I've had enough of that. Turn that off.
It's like music and dance.
It's a little bit uncomfortable.
Why is there smoke coming from your hair?
I thought you were being serious. The applications for this are endless. Think about it. For sports, they're already using it in snowboarding. Imagine for golfing, the perfection of the golfing swing, and also for physiotherapy. Genius.
It's really good. I'm not sure about your vibro... what's it called?
Tactile
technology.
It's genius. What do you mean? Look at it.
No, it's good. Wearable computers are big news, as is AI, artificial intelligence, computers, robots, thinking, behaving like humans. Have a look at this. This is called AI Con, and it's been developed by a team at Goldsmiths in London, a team of both artists and computer developers, and that's really important. The idea is that it can actually mimic the way that a human being can sketch a human face. Now have a look at this. It's actually doing a little sketch of me. So what you've got a robot arm that's controlled by these little servo motors and just a regular old pen. Here's a little camera so we can actually take a picture, all hooked up to a regular old PC, which has got face detection system in here. And it's doing a pretty good likeness, but the idea is not to do a photographic representation of my face. It wants to think like the artist thinks. It wants to draw like the artist draws. Now, you may think this looks very simple, but getting a computer and a robot to see like a human, to think like a human, to draw like a human is an incredibly complex activity. I think this is really, really exciting.
I think that's amazing too. Yeah. But I'd like to go from drawing stuff to making stuff. This is effectively a three-dimensional printer. Whereas a normal printer just draws a line, this draws a line in a very thin layer of melted plastic, and then as it's setting, it draws another line on top until it can build it up to produce just about any shape. It's like it's icing a cake. You can see that little layer of melted plastic being dropped down on there. Now, I'm slightly affecting the process, so I'll drop that back. Now, these are relatively simple objects compared with this. This was printed by a printer. And imagine trying to make that any other way. It's so complicated. Now, this machine generally works in plastic and clay, but there are similar machines that take on the really difficult materials, like stainless steel and titanium. And that opens up a whole world of manufacture.
Now take a look at this. This is very cool. It's called a Sentium platform, and it's the latest in the new wave of wireless medical monitoring devices. Now it's attached to me using a regular ECG electrode, and it's monitoring everything from my heart rate, my body temperature, my movement, my breathing, and transmitting all of that information in real time to wherever that needs to be. In this case, this computer right here, but of course you can transmit the information much further distances. For example, these devices were used in an expedition to the Antarctic, and they beamed the information straight back to the UK using satellites, and something very similar to this was used during the Chilean miners' disaster. Now, the future of this technology is very exciting because the next generation of these little fellas will be disposable. So think about it. You could have a plaster on a patient monitoring all of their vital signs, and it would require so little energy that it could work for 5 days straight and be so cheap that you could actually just chuck it out afterwards, or better yet, recycle it.
Very good. Those are going to be brilliant. Very good indeed. Now, have a little look at this. Lots of us have got old bits of exercise equipment gathering dust in our basements, under our beds. But I guarantee you, nobody has got anything like this. A Dr. Yan under their beds.
Hello, Thomas.
Hello, how are you?
Oh, I'm fine, actually.
Now, this is clearly a swim simulator.
It is indeed.
What does it feel like?
Well, it doesn't feel exactly like swimming, I must say. But you remember those rowing machines that we used when we were doing that calorie item?
Yeah.
Well, I've basically got one of those attached to each of my limbs.
So it's the same, it's the same principle. You've got these rotating fans that give you resistance.
Exactly. And you can tell how much power I'm putting in for each limb. So for an elite swimmer, I guess, who wants to know how much power and how much energy that they're kicking out, as it were, then you can use this.
Now, would this be good for somebody like a novice who's practicing, like learning your stroke technique, that kind of thing?
Well, the researchers at Canterbury Christchurch University reckon it's just for elite athletes, like for the Olympics and things like that, who really want to work out where they're putting the energy in so that they can improve their strokes.
So it's all hooked up to a computer, so we can read all about it down there.
I can read out how much I can set myself targets.
OK. I'm going to let you carry on. Fantastic.
You do that.
OK, then moving swiftly on, rather surreally, from Dr. Yan, as if by magic, to Dr. Yan.
Take a look at this. Good, isn't it? But I can tell you, it doesn't always work so well. Now, clearly there's a technique to making that work, but behind that is a lot of science, and it's to do with friction. Now, that's the force that makes it difficult to slide one surface past another. We're all familiar with friction. It's why the soles of my shoes grip the floor so I can walk. But how exactly does it work? Well, it's all to do with surfaces. You see, even a relatively smooth surface like the bottom of this vase is covered in microscopic irregularities like bumps and so on. And that means that when any two surfaces meet, then those bumps can interlock, a bit like these egg cartons. And it's really hard to slide one past the other because those bumps obstruct one another. And that's one of the ways in which friction can come about. Now, different materials have different numbers and sizes of bumps. So when I use this rough wool felt, well, let's see what happens. Not so good. Now, that's because the surface of this felt is absolutely covered in tiny little bumps. And when they're pulled over the bumps in the surface of the glass, you get that obstruction and lots of friction. This means the vase stays stuck to the cloth, and as the cloth's pulled, it drags the vase along until it falls. But watch what happens if I try using something a lot more slippery. Silk. Now, although it may feel like silk is bump-free, it does actually have microscopic bumps on it. It's just that they're smaller than those on the felt. And so there's less of a physical obstruction for the bumps on the glass to push against. The vase does move a tiny bit because it's impossible to get rid of all the friction. But the cloth is gone before it falls over. And then the friction of the table just stops it dead. So slippery is best, but that's not all. The yank is critical. Too slow, and, well, I'll show you what happens. Even with low friction silk, a slow pull gives the friction long enough to get the vase moving, and eventually it gets pulled over. But by pulling fast, the whole thing is over quicker. The cloth is cleared before the vase builds up speed, and it just stops on the table. But what's really interesting is that bumps and obstruction are not the only thing involved in friction. There's a load of new stuff we're only just starting to find out. And in fact, it's a really hot area of research.
Excellent film there from Yan, but as an enthusiastic amateur magician myself, I thought I'd better have a go at that, test it out. But I'm going to up the ante. Yan, single vase of flowers. Yeah. I'm going for the whole tea set.
Are you serious? You're going to do that now?
That's the point. We've got to test things out, so I'm going to test it out and see if it works.
I'm mildly incredulous.
There is a small chance this may go wrong.
Have you practiced?
No. But I don't want to contaminate my purity by practicing. Let's just have a go. Are you ready for this?
Yeah.
Oh my. Okay, ready? Drum roll, please. In 3, 2, 1.
Come on!
The legend!
I want to see that again. Let's have a look at that.
That was sweet. Campbell, that's amazing.
That was good.
You must have an incredible intuitive understanding of friction, inertia, and centres of gravity.
Magic. What are you talking about?
No, it's not magic at all. Not only did we do that, they didn't move an inch.
They didn't move at all.
Motionless.
At all.
That was very good anyway, so there you go.
Whoa, I'm really impressed. Well done, you.
Now, recycling. We all know it's important, yet it seems every local council has a different policy as to how it should be done. I mean, for me, I've got to put a bunch of stuff in one box, and then glass in another, and batteries in a little bag. What about you guys?
Well, we've got one box for everything, but it's annoying because there's limits to what you can and can't recycle. Some things you can't recycle, some things you can. But most things in my house, certainly, are recyclable, but our box is only about yay big, so there's just not enough space.
Yeah, same for me. I've only got one box, not enough room to put everything in. And I'm confused as to why the bottom of a plastic container can be recycled, but the film can't.
Exactly.
Tetra Paks can't. Oh, actually, they can now because there's plastic in them. It's all a bit annoying, really.
It is, and there's sort of two schools of thought on it. One is if householders themselves are responsible for recycling, then you get a better quality of recycled product. Whereas if they're not responsible, if they chuck it all in one box, at least more people will do it.
So you think they kind of balance each other out,
Yeah.
those two things. That's interesting.
But if you watch this, there might be a solution to that conundrum.
Trillions of tins, a plethora of plastic, piles of paper to reach the moon. I'm not talking about the recycling stacked up in my kitchen. As a nation, we're recycling more household waste than ever. And government targets are demanding that by 2020, we recycle half of all our waste. One way of persuading people to recycle more is to make it easier, by asking them to chuck it all in one big box instead of sorting it all into separate containers. But there's a price to pay, because somewhere further down the line, someone has always had to sort it all out. Until now.
Hidden within this thundering mass of blue steel are all manner of cunning devices to convert millions of tons of rubbish into millions of tons of very valuable raw materials. With the right kit, that pile over there is like having a veritable gold mine.
This state-of-the-art depot in West Sussex is one of a new generation where technology does the sorting for us, producing vast bales of single materials worth up to £450 each. First port of call is the trommel, a revolving sieve that skims off the large sheets of paper. Everything else goes on to a sort of gold panning machine.
All the flat stuff gets rocked up to the top and the rounder stuff rolls to the bottom.
The torrent of trash then has the metal removed.
It looks weirdly magical there, but all it is a very powerful magnetic field that plucks out anything with iron or steel in it.
The metal left behind is mainly aluminium, which heads on to encounter a much stranger magnetic effect. Now, magnets don't normally attract aluminium, but they do affect it another way.
As a magnet moves past a conducting metal like aluminium, it produces an electric current in there, and then that electric current produces its own magnetic field, which interacts with the magnetic field from the magnet, causing movement. And it's exactly what they're doing up there, creating magnetic fields in the aluminium, making the aluminium jump off to somewhere they can catch it and separate it. There we go. Just a little lid from a yogurt pot, but it's aluminium, which is a very valuable resource. It's difficult and expensive to extract. It's worth quite a lot of money.
Though it may be just 1% by weight of a household recycling box, aluminium could make up a quarter of its value. The bulk of most people's recycling is another material, plastic. But that has always proved the hardest resource to sort.
To cope with increasing amounts of recycling, they've installed this ingenious device here. It's like an electronic eye that's linked up to a compressed air shooting gallery. Sorting plastics used to be a manual job, and it's very difficult to spot the differences between them. Whereas this machine here uses infrared light. It shines it down on all the rubbish going underneath. Then whatever's reflected is analysed And if it's the kind of reflection that will come off the right kind of plastic, then a signal sends some compressed air jets that then fire it to a different conveyor belt. It does an amazing job at quite astonishing speed.
But as advanced as this machine may be, it's not working at its full potential. Currently, this place only sorts plastic bottles from the mixed waste.
What happens to things like little yoghurt pots? Because I've not seen any of those make it through.
Unfortunately, there's no secure, sustainable market for them to go off to be recycled. They're often made up of a mixture of plastic, maybe 2 or 3 different types of plastic in a single yoghurt pot, which is why it makes it very hard for them to be recycled into new products.
So all that recycling is kind of pointless unless there's an end user for what you've sorted out.
Exactly. We are set up ready to go. We can separate out the individual types of plastic, but there's very few people who would accept them for recycling at this moment in time.
But recycling fans shouldn't fret. Gradually, that market for mixed plastic is growing, which is why some councils are starting to take all your yoghurt pots and takeaway trays. So if you don't recycle them at the moment, you should be able to soon.
If plants like this continue to prove the viability of mechanised sorting, then domestic recycling could become a whole load easier for all of us in the future.
That looks like a bit of a success story, doesn't it? I can't help thinking, though, how much money you could save if you didn't have to build a plant like that in the first place and we all separated all our recyclables at source, you know, at home.
I agree with you, but it's a bit of a cycling utopia. I mean, the reality of it is where they've implemented those schemes, people just aren't recycling as much.
Got to change attitudes.
Yeah, but I think what's interesting is the fact that if there isn't a clear, financial market for a particular project, it's just not going to be recycled. It's just going to end up in landfill. And ultimately, it kind of sounds corny, but it's up to consumers to decide what they buy in terms of packaging, I guess.
Very good point. But also the providers, also the suppliers as well.
That is the crux of the matter. It's the finance that really governs all of this. And there are solid markets for aluminium, glass, steel, paper, but there are just certain types of plastic that nobody wants.
It's the plastics that are a problem. OK, well, that's it from us. Time to say goodbye, boys.
Oh, bye-bye. See you soon.
See you soon. Hey, can I have a go at the tablecloth trick?
Of course you can.
Do this.
You can do it. It's easy.
Okay.
You can do it.
Well, think about it. Just do it.
Yeah, just think about it. 1, 2, 3.
2, 3.
Oh!
Genius.
Yours, I believe.